Okay, let's dive right into this explainer. We're looking at an absolutely fascinating publication from April 23, 2026, by independent researcher Stephen D.P. Moore. This work literally flips everything we think we know about computational geometry completely on its head. We're talking about a brand new, discrete object-oriented modeling system that might just change how you view the entire physical world.
Think about it for a second. We all grew up learning that to find a circle's circumference, you absolutely have to rely on pi, right? That continuous, infinite, real number. But what if that's not the only way? What if there's a totally different, maybe even more fundamental way to map reality? One that doesn't rely on decimals that just stretch out forever.
There's actually a pretty stark contrast between these two paradigms. Traditional geometry relies heavily on continuous coordinate systems, think Cartesian planes or space-time metrics, which often bleed into negative or non-natural numbers. But Moore's breakthrough transitions us completely away from that. He introduces a discrete relational geometry. Basically, he's building a system entirely out of natural numbers, fixed points anchored in a relational model, and a totally new ordered proportion theory. It's a completely object-oriented approach to math.
Moving right into Section 1, extending Euclid and his original geometric vision. To really grasp this paradigm shift, we actually need to step back thousands of years to the very foundation of geometry itself.
That quote is straight out of Book 1 of Euclid's Elements. You see, Euclid originally used magnitudes and geometric relationships rather than our modern infinite metrics. To him, a point was just an unquantified spatial node. Well, Moore's new theory revitalizes this exact classical vision. He takes Euclid's theory of proportion and builds upon this Euclidean geometry to create a modern, natural-valued object modeling tool using discrete elements.
The tricky part with our modern tools is that traditional coordinate systems really struggle to represent static, non-Euclidean geometry without leaning on continuous manifolds. Space-time links space and time with continuous motion, and Cartesian coordinates kind of force you into abstract negative values. Moore's framework totally escapes those limits. It uses strings of relational elements that don't span space-time or have mass. Instead, they connect zero-dimensional nodes in a discrete, highly structured way.
This brings us to Section 2, the relational unit circle, which is a completely new way to map. This is really Moore's core innovation and the absolute heart of this explainer, constructing a circle starting from just a single, fixed point. Instead of relying on abstract real numbers, this system uses something called ordered proportions. Think of an ordered proportion like a bridge. It's a structural coupling that links two independent geometric proportions together. So if you vary the linear geometry, you automatically induce a variation in the rotational geometry because they share discrete geometric magnitudes. They're locked together. And this brilliantly illustrates that relational unit circle. Here, the linear radius and the angular rotation are inextricably connected. Moore reveals a strict 4-to-1 proportional equivalence between the discrete angular steps and the linear radius. You basically have 4 equal linear symmetry segments that correspond precisely to one full angular rotation. And the crazy part, this is completely independent of real number or traditional arc-length geometry. It is completely unique from the classic ratio of 1 to pi for measuring a standard unit circle.
Because this system uses discrete, natural value counts, the radius and the circle's circumference are constructed from the exact same relational units. In classical math, those two are incommensurable. You can't measure both perfectly with the same ruler because, well, pi gets in the way. But here, everything is perfectly scaled, intact, and totally commensurable, using shared fixed points and a unified 3-4-5 Pythagorean structural coupling.
Let's look at Section 3, Earth as Pyramid, Mapping Physical Objects. It's one thing to talk about abstract math, right? But what happens when we apply this object-oriented framework to a massive, real-world object like our very own planet? Moore tests his theory by building crystallographic-like sets of points to trace the dimensional ratios of objects. He starts by defining a fixed spatial point on Earth, like the North Pole. Then, he partitions Earth's actual polar and equatorial dimensions into primitive relational units. Finally, he executes 6 discrete translations upward along the z-axis. By moving these points vertically in precise increments, he builds a 3-dimensional lattice. And the result of mapping Earth's primitive elements onto this discrete 3D lattice naturally generates a basic square pyramid. 3-dimensional space emerges simply from the perpendicular composition of these relational 2-dimensional planes. It's literally a geometric blueprint for a physical structure derived entirely from Earth's exact dimensions. When you calculate the dimensions of this theoretical Earth pyramid model, something incredible pops out. The calculations scale down flawlessly, at a precise ratio of 1 to 43,200 relative to Earth's actual radius and trace circumference. This ratio reflects a fundamental proportional relationship that's just inherent in the geometric partitioning operations Moore discovered.
This leads us perfectly into Section 4, the Khufu connection in ancient architecture. Prepare yourselves for the ultimate historical twist, where this cutting-edge 2026 mathematical blueprint collides with some of the most famous architecture in human history.
So back in 1883, the famed Egyptologist Sir William Flinders Petrie conducted an incredibly precise survey of the Great Pyramid of Khufu at Giza. Petrie noted the builder's profound attention to square measure and complex geometric proportions. He realized the dimensions of the pyramid weren't just arbitrary, they were part of a highly deliberate uniform mathematical system.
The alignment here becomes absolutely staggering when Moore cross-references his purely theoretical Earth pyramid against Petrie's real-world measurements. The margin of difference is incredibly small. The base perimeter is off by barely 1.43%. The circumference trace difference is about 0.5%, and the original height varies by just 0.71%. The Pyramid of Khufu is mathematically echoing the exact same qualities of Earth.
So what do we make of those tiny, less than 1% deviations? Well, Moore suggests that rather than being ancient construction errors, the slight indented distortions in Khufu's base might actually be intentional. They could be geometric variations meant to represent natural forces, like Poisson's effect or the Earth's centrifugal rotation, encoded directly into the stone itself. But this isn't just about solving ancient mysteries, as cool as that is. This discrete, object-oriented modeling system opens massive new doors for modern science. Because it works without continuous metrics, it could revolutionize crystallography by modeling complex lattices perfectly. It could help map the icosahedral geometry of viral capsids, like adenoviruses. We could even apply it to decode the relative dimensional properties of exoplanets and distant moons. It all leaves us with a profound, almost dizzying question. If Moore's April 2026 relational geometry perfectly generates the dimensions of the Great Pyramid using the exact proportions of the Earth, does this mean the architects of the ancient world intuitively understood the discrete relational structure of reality millennia before we built computers to figure it out? It is definitely something that will change how you look at the geometry of our entire universe.